Our next speaker is Benjamin Bross. He's a project manager at the Fraunhofer Heinrich-Hertz Institute. Is here? Okay, good. Come set up. So at the Heinrich-Hertz Institute, he's currently responsible for the development of H.265, H.265, real-time encoders and decoders. Since the development of the new H.265 coding standard has started in 2010, he has been very active in the standardization process as a technical contributor and coordinator of core experiments. In July 2012, he was appointed as co-chair of the editing ad hoc group and became the chief editor of the H.265 H.265 video coding standard.
Yeah, thanks Alex for the introduction. So I will talk a little bit about the new H.265 or MPEG-H video compression standard, and here I will focus mainly on some performance results. So we heard a little bit about royalty-free codecs, and so I will skip that part and just tell you what's the compression efficiency and the coding performance of that new standard compared to other video compression standards and technologies. And where we'll especially focus on is the low delay performance. So this is research a colleague of mine recently published with a comparison of compression efficiency under low delay conditions. So it's a little bit different than coding conditions you would use to code movies, to store on a Blu-ray, or to put on YouTube. And then I will have one slide on the extension, so what is happening after version 1 of the standard was finalized, and at the end some picture slide show that I called H.265 Evolving Fast, with some pictures and dates on a timeline what happened in the last year and this year regarding H.265 implementations. So what is H.265? Just to refresh your memory. That's the last joint video compression standard from ITUT and ISO. From the ISO, it's the MPEG group. It's a little bit confusing with all the names, so here are both names. Though H.265 is the ITU name, and MPEG-H, or the 23008-2 is the ISO number for that standard. So it's basically the common name is H.265. And so Fraunhofer HHI, so our institute, contributed main techniques to that standard. Among these are the coding block, variable block size for coding, prediction, and transform of this hybrid video codec, including the residual quad tree, prediction block merging concept, and new concept in transform coding, and the well-known concept of Kabak entropy coding, which was already introduced in the H.264 standard by Fraunhofer HHI. So that's basically where I worked in the development part of the standard, and as an editor I wrote the text specification of that standard, and now we're trying to offer solutions for encoding, decoding, using H.265 to further deploy that standard and help the industry to fastly adopt the standard. So the pitch was 50% bitrate reduction over H.264 for the same subjective image quality, and that's what we achieved at the end of the standardization. The version 1, so the first version of the standard, was finalized in January last year. And it started with 3 main profiles. They are all pretty similar, only it's the main profile has 8-bit, the main 10 profile goes up to 10-bit, and their main still picture profile is the same as the main profile, but only consists of 1 picture. So this is what's currently discussed in JPEG for still image coding. So this was the first version, and I go to the next slides where I report coding efficiency result for these. So that's the question, what's the coding efficiency? So the pitch was 50%, and mostly, or during standardization, besides intra only, we looked at 2 configurations. One configuration is what I call here, and what is called in the first comparisons in literature entertainment. So this is the classic coding structure used for TV, movies, storage, and streaming of movies, video on demand, what I listed here. And it's a hierarchical B picture structure with random access every, around 1 second. So each second you could tune in the video. It's like fast forward and like navigating in the video. Then an interactive configuration. This is for video conferencing. This has to be a very low delay picture structure for the coding with no structural delay, so no picture reordering, and just like one picture referencing previous pictures. So here is a summary or a table where I summarized already performed comparisons in literature, starting with a paper with my colleagues and Jens Ohm, who's also chairing the joint video team that was developing HEVC, released in December 2012, so like 1 month before we actually finalized the standards. And they reported two kinds of results. Objective results, so what's the bitrate savings for the same objective quality? That's based on the PSNR measurement. And with subjective testing, what are the bitrate saving for the same subjective quality in terms of MOS score? And the codecs or the configurations they analyzed here was an entertainment configuration compared to H.264 AVC and an interactive low delay configuration also compared to H.264 AVC, but there were only objective results based on PSNR reported. So what we can see here is that from an objective point of view, we have 32% bitrate savings for the same objective quality, so for the same PSNR value, but subjectively, where the subjective test was carried out by an independent test lab with non-experts, we ended up with 50% bitrate savings compared to H.264. So that's what satisfied the pitch for H.265. So here you can see that also the PSNR as an objective measure of quality is a little bit pessimistic. So when you go to the interactive configuration, you see that the bitrate savings for H.265 over H.264 is 40% in terms of PSNR, and when you would extrapolate that, you would end up with also a little bit more than 50% when taking subjective quality measurement. So the next ones are for the entertainment configuration that a colleague of mine, Dan Groys, performed as a comparison between H.265 and H.264 as well as VP9. So this is for the random access entertainment configuration with 1 second random access, hierarchical B picture, structural delay in the coding structure, and they found out for an entertainment configuration you have a bitrate savings of 39% objectively, and for VP9 it was 43%. So these are the numbers that we found out, and that other companies who also investigated or compared these codecs with publicly available configurations and software turned out to end up with this number. The difference, so why they're different when you compare H.264 from the first and the second, is the encoder used for H.264. And the first comparison, that's what you see in the last columns. For H.264 AVC, used the reference, the JSVM reference encoder, which is very, very, very slow, but also pretty efficient because it's trying all modes. And the other comparison of my colleague Dan, he used X264 as a real-time encoder, so like a really fast optimized implementation of H.264, and that's why it's a little bit, you get a little bit less coding efficiency or more bitrate savings for HEVC because you use like an optimized real-world implementation of the codec. Then there was a subjective comparison for the entertainment configuration for H.264 and VP9. It's performed by Turaj Ibrahimi's team at EPFL, and it turned out subjectively HEVC compared to H.264 AVC for 4K, so for Ultra HD sequences, we end up with subjectively more than 50% bitrate savings for the same subjective quality. And for VP9, it's 50%, so 49%. So actually, for the same subjective quality, for 4K Ultra HD video, we have, compared to VP9, 50% bitrate savings, according to the study from EPFL. And then last but not least, this is where I will further focus on the next slides, are the results for the interactive configuration, let's say a low delay configuration where we have 41% objective and 32% objective bitrate savings for HEVC compared to H.264 VP9. Okay, so here are the encoders that have been tested, because that's if you compare codecs, it's a very important thing to be careful with the encoder configurations and the encoder you're using. You could use, for example, an H.264 encoder with a very bad configuration, or here use a low delay configuration, and then for H.265 or HEVC, you use a random access configuration with hierarchical B pictures. That would not be a fair comparison. So what my colleague Dan was trying to make sure is that you have the same configuration, the same optimizations for each encoder that was used in that comparison. So for H.265 HEVC, it was the HM reference encoder, very, very slow, but that's the best quality you can get. For H.264, it was the X264, the open source, very fast and the most efficient and the fastest open source implementation of H.264 encoders now available. And for VP9, it was the WebM official VP9 encoder after the bitstream format was finalized. So coding structure was an IPPP, so P pictures, no B pictures, and purely low delay coding structure. So an initial I picture at the beginning, followed by only P pictures. The test sequences in that particular evaluation were the Class E video conferencing test sequences. Maybe Alex, you can remember some of these sequences. They are the Class E sequences from the JCT VC that we used in standardization. So from the content and from the setting, it's classical video conferencing content in these three sequences. The resolution is 720p60, so 60 Hertz. And the encoder settings, which I already mentioned, to somehow equal them, to have a fair comparison of two codecs. So the X264 settings were chosen for an optimized PSNR. You can also optimize for different values, but the criteria of this comparison is objective PSNR. To be fair, you have to optimize the codecs also for PSNR and not for another thing, so they give the best results for that particular measurement. VP9 settings were the settings recommended by the developers. And VP9, according to their assessment, was not optimized for one-pass coding, but for the development of VP9, they always assumed two-pass encoding. And so Dan said, yeah, okay, we will get the best configuration for VP9 and enable two-pass encoding, which is clearly no low delay. You don't have two-pass encoding, but we want to get the best results, to be fair. And if it's not optimized for one pass, let's use the optimized version, to be fair. So that's why additionally two-pass results were provided for VP9 and for X264. The bit rates were ranging from 0.2 megabits per second, so 200 kilobits, up to 4 megabits per second, with these constant quantizer QP values from 22, 27, 32, and 37. They are resulting in 4 bitrate points, and for each of these bitrate points you get a PSNR value, which you can see in these plots here. So starting from the, let's say, 200 kilobits up to 4 megabits. There are sequences where you reach 4 megabits, but in that range for all 3 sequences the PSNR was measured, and then you get such a nice rate distortion plot. And you see here that for the same, you can view it from both sides. So for the same bit rate, you get, for example, for H.265 compared to H.264, a better quality, or for the same quality, you get much lower bit rate. So you can view it from both sides. The measurement that was, or that will be cited in the next slide is the BD rate. So for the same PSNR, what are the bit rates? Or what is the bitrate reduction, or how it's reported in the next slide. For the same PSNR, what is the bitrate overhead for VP9 and H.264? So how more bits you need to spend with all the other codecs. So that's the Bjørntegard delta rate that is reported in %. And here, I tried to put that in this particular plot, where I also on a logarithmic scale put in the encoding speed up. And here you can see that the HM reference encoder is not an optimized implementation. It was used in standardization to somehow show the performance of H.265, and there are no optimizations in it. So when you see VP9, it's about 3 to 7 times faster than the HM reference encoder, while the really fast H.264 is over 2,000 times faster than the HM reference encoder. And you see also the results for 1-pass and 2-pass. For VP9, there's actually not much difference between 1-pass and 2-pass, so that's the settings we got from the developers, and that are the results we received with these optimized settings. So you see there's not much difference between 1-pass or 2-pass. The overhead, so this is what is on the x-axis. So for the same objective PSNR value, quality values, you have for VP9 48% more bits, and for H.264 you have 73% more bits than with the HM reference encoder. So you see VP9 in that case is clearly better than H.264, but for this test cannot reach the H.265 performance. That's the second point I already mentioned. Second pass encoding does not gain much for low delay. For a random access configuration, that might be different, but for this particular case in low delay, not. And the runtime differences are also very varying from VP9 to H.264. So some thoughts on the encoders. All the encoders that are used in that comparison are publicly available. So with the configuration cited in that paper, everyone can reproduce these results. 2-pass encoding in VP9 is faster than 1-pass encoding. So maybe that's the point where they optimized it for 2-pass encoding, because it's actually faster than 1-pass. All 3 encoders represent different levels of optimizations. So HM reference software has no optimizations. VP9 has some code optimizations, while H.264 is highly optimized. And so real-time encoders optimized for low delay are expected to achieve the same coding efficiency like the HM reference software in the next years. That's what we observed for H.264, and that's what we expect for H.265. So this is the scenario. And where I can get to H.265 evolving fast. The extensions, in April this year, we have the range extensions for higher bit depth, more chroma formats, 444, 422, while the first version was all 420. Multi-view, so the 2-view 3D extension was finalized in July this year. Also scalable coding in July this year, but maybe Vidya will talk on that or give you more details on the scalable extension. And next year, the last extensions to be finalized is the 3D H.265 extension, so real 3D, multi-view, and depth. So evolving fast, that's the picture slideshow. That is the Geneva ITUT meeting where we finalized H.265 version 1. So that's the whole JCTVC group that worked on the standard. So this was January 2013 in Geneva. H.265 was finalized in April on NAB. We showed a 4K UHD live software decoder as a first implementation for UHD from our academic point of view and our small booth at NAB. Then at IBC we showed a HD live software encoder with a camera setting and like 3 clients for HD. So this year actually at Mobile World Congress, together with our mobile networks division, we showed H.265 HD live encoding over LTE network. So we had a channel in the box with an LTE sender and receiver. So a small base station in a box to make sure that we do not build up an LTE network in the show. So HD over that network we showed. In April, we had a first end-to-end full 4K Ultra HD live broadcast with Sky Deutschland, a soccer game from the soccer area field in Munich. So this was the first successful end-to-end 4K broadcast using our software encoder. So this 4K live broadcast with 6 4K cameras, check, this is done. At IBC, we demonstrated the 4K Ultra HD live software encoder with a coding efficiency that comes close to HM reference software. So there we are with real-time implementations. And just on a side note, that's what I found in the specs for the new iPhones. FaceTime over cellular uses H.265. So in the next generation mobile phones, you also have for video call encoding, decoding H.265. It's just an example. Yeah, summary, several studies confirmed the 60% bitrate savings for H.265 over H.264. We have significant bitrate reductions compared to H.264 and also VP9 for H.265. In this particular example for low delay applications. 1.5 years after finalization of the H.265. So really you have to imagine that it was last year in January that like the text was done and finalized describing the bitstream syntax of that new standard. And only 1.5 years after that, real-time encoders are approaching the coding efficiency of the HM encoder, so the really, really slow reference implementation encoder. And from our HHI Fraunhofer side, we will continue research on H.265. So provide solutions, efficient encoding, decoding solutions for the industry to deploy the H.265 standard, as well as continue our research on the next generation video coding. So here are the sources and the references from the comparison I cited. And that was it. So thank you for your attention. Now we have time for questions.
Excellent, excellent. Questions? Robert.
So you mentioned that you get close to the compression efficiency as HM in real-time encoding. So how does that compare to H.264? Because the graph you showed before in the paper, it was still like a factor of, I think, 6,000 or so. Yeah. So where are you with the demos you presented? Okay, the demos were all real-time. So at IBC, it was 60 frames per second, 4K UHD. So this was real-time. But I have to say, and here comes the but,
We use 2 servers with overall 96 physical CPU cores. So you still need quite some computing power to do that. But I think we will have a next talk that will talk about hardware architectures where you can do that. For us, it was just like, let's use 2 servers to show the maximum. That is just to show that it's possible to compress video with H.265 with that amazing compression efficiency in real time. And when it needs 2 4-socket Xeon servers, let's use that. It's just like to show that it's possible. Moore's law will continue, hardware implementations will show up. So that was just like the proof of concept. It is possible to do that in real time.
Thank you.
Sure.
Thank you. I have a question relating to the following point. In speech coding, like EVS, we had the presentation about this just before. Traditionally, C code is published for encoder and decoder to guarantee quality. Now, in video, that is not the case usually because the concept is broadcast-like, so that there are many decoders and a few encoders. Now, in case of video telephony, of course, that is not true. So, by this reason, IMTC Media Processing Activity Group published source code for H.264 years ago to catalyze this process. So, your comments on this relating to H.265 would be welcome.
Okay, so for the reference encoder, code is publicly available, so it's provided on our servers. You can download the reference encoder and decoder source code. It's not C, but it's procedural C++, so it's not fancy class structures or objective-based programming, so it's procedural C++, and you can download it. But it's a reference implementation, so it's not meant to run in real time, because in standardization we focused on the coding compression, the coding efficiency to achieve that 50%, and so none of the companies developing that standard wanted to spend resources on like really optimizing the reference code. And if you highly optimize it, it's not that readable for people who want to try to understand the algorithms that are introduced. So it's also made for readability. But we welcome every open source real-time implementation. There is a decoder implementation that is open source. It's called OpenH.EVC, and that is now integrated in the VLC player. And that achieves HD real-time decoding, so that's available right now.
Other question? No? Okay. Thank you very much.
Okay.
That's great.
Thanks.
Thank you.